Okay, I want to begin with one little addition to what we've talked about before when we defined our vector space, which implied the existence of our dual space, which are vector space basis and our dual space basis, and all the other things that go along with these things. We mentioned that, well, one of the key things was we mentioned that we would create an inner product. This inner product implied the existence of a metric tensor, which was an element of the tensor product space of two constructed by two dual spaces, which was a 0, 2 tensor product space, and sometimes that's called T 0, 2. And this metric tensor mimics this inner product. The question is if the dual space automatically exists no matter what once you kind of create the vector space, when you create this inner product in the vector space, do you create an inner product in the dual space? And the answer is sure. The logic is pretty straightforward. This metric tensor and this inner product has allowed us to establish a correspondence between vectors in the vector space and covectors in the dual space. And by our index gymnastics lesson that we did last time, we now know that if I have the vector A mu E mu, that this simply corresponds to the covector A mu E mu through the rule that A mu equals, say, A nu G nu mu, something like that. And this is sort of by definition, we call the covariant version of the components equal to the contravariant contravariant components multiplied by the metric tensor using the Einstein summation convention on these mu's. So once we have that, we've established a correspondence between vectors and covectors. So now all we have to do is say, well, if I have two vectors and I run the inner product, nu E nu, like that, I want that to equal some inner product of the covectors. And we know this inner product, and we know the relationship between these components, right? So that will derive for us this inner product. And this inner product exists. This inner product takes two covectors. So it's an inner product on the covector space. And that's the connection between the two. And through this, you can create the rule of how the covector basis needs to work. And it should be no surprise that that this whole thing is going to demand that E mu E nu equals E mu E nu. And so that establishes a covector inner product. And we could actually make a little star so we're not confused about what these parentheses mean. The star is associated with the covector space. They don't usually do that, but understand that this inner product is not the same as that. It's not the same because it takes different elements. It has a different domain. Its domain is the covector space. Okay, so that, and therefore, by the way, this all implies that there is a metric tensor associated with this vector product, this vector space, which we call the covector space, and that is an object that lives in this tensor product space, which is T2, 0, and it's given, no surprise, by G mu nu E mu E nu. And this is the metric tensor with raised components. The metric tensor with raised components lives in a different tensor product space than the metric tensor with lower components. The metric tensor with mixed components will live in V star, right? That one would be, if you did that, that would be G mu nu E mu E nu, something like that. And but the point being that all of these objects live in different sets, different vector spaces. And remember, tensor product spaces are vector spaces too. Everything's a vector space, and so, you know, when I've got to stop worrying about pointing that out all the time. I have to assume that that's something you understand. Vector space, vector space, vector space, vector space. Tensors are vectors. We kind of went through that little ironic nomenclature curiosity much earlier. But this explains everything. This explains the inner product on both spaces. This explains the metric tensor in the fully, this is called the fully covariant form. The components are fully covariant. And here the components are fully contravariant. And we went through what covariance and contravariant meant in terms of transformations, linear transformations on the basis. And we did that in a previous lecture. Okay, so I'm going to pause with that, and we're now going to discuss a very, very, very important specific vector space. And that's going to be the next part of this lecture. All right, now so far, when we've created our vector space, I've kind of been putting everything in a box, right? The vector space, the basis of the vector space. Oops, geez, I've already screwed it up, right? The basis of the vector space, the fact that it's a real vector space, the number of dimensions is 4. I've done all that, and there's a lot of things that you need to just automatically know at this point. You automatically know that there's a dual space. You automatically know that there's a whole infinity of tensor product spaces, and the logic of all of those things appears out of nowhere. Meaning it appears automatically once I produce the vector space. You don't need to add anything new. And then, of course, I've told you that we're going to add an inner product, and from this we develop ultimately the equivalent metric tensor, right? So all of these things, whenever I say we have a vector space V, an inner product space V, I have to sort of assert that it's an inner product space, your mind has to create all of that other stuff as mathematically existing as well. All of those things come into existence naturally with no extra benefit. Once you have the inner product there, you get the metric, you get the tensor product spaces, everything flows. Now, but what we've done is we've been very abstract. I mean, this has been a very abstract study. We've been talking about the vectors. The only specific vectors we really talk about are the basis vectors, and we just give them sort of symbolic identities, right? We give them the symbolic identity E0, E1, E2, and E3. These are just little objects. I mean, these are typographical symbols. These are glyphs. And we're basically saying, well, a general vector is you take this glyph and you use this rule and you create more glyphs, and all of these glyphs behave in a way that is mathematically consistent, and we're going to call this whole thing the study of vector spaces, or whatever we're going to call it. And the idea is now, what are vectors? In physics, we have notions of force, right, and velocity, and those things are vectors. And now, and in our old study, our original study of mathematics, vectors were these little pointy things. And we understand now how those little pointy things are vectors, because they can be added together, they can be multiplied by real numbers. There are vectors that are opposite of vectors that sum to 0. We know how to add them, and we understand basis vectors, right? We can make basis vectors. And any vector can be created as a component of basis vectors. So we understand all that, but we've not touched on any kind of, and the word is realization of a vector space. And this is absolutely important to understanding general relativity and moving on. Realizations are some kind of mathematical objects that behave like vector spaces. And in this case, we're looking for mathematical objects that behave like 4-dimensional vector spaces. And all we need are things that can obey those rules where there's vector addition, where there's scalar multiplication through the real numbers, where there's an opposite, I'll call that the plus-minus rule, right, where you can add things to 0, and there's a 0 vector, and it's a set of all of those things together, and it's all closed. Right? We're looking for mathematical objects that behave under these rules. These little symbols, E0, E1, E2, and E3, they behaved under the rules by definition. I asserted that any sum of those things was in the set. I asserted that any product of those things was in the set. So by definition, these things obey the rules because we made them that way. So now we need to find some things out there that obey these rules because of what they are, kind of like the little pointy things. And we're going to go right to the most important one. and that important one is called the differential operator. So we're going to start by imagining a function. And I'm going to make this a function of 4 variables, x0, x1, x2, and x3. And sometimes I'm just going to write that as f of x mu, or sometimes we'll even write it as just f of x, where we understand that x is actually x mu, which is actually x0, x1, x2, and x3. It's 4 different numbers, but it's a function of 4 independent variables that are kind of bound together symbolically by x. And of course, ultimately, these are going to be called coordinates. And they're going to be space-time coordinates, right? But right now, let's just think of it as a function of 4 variables. And any function of 4 variables can be, if it's a differentiable function, we're only interested in differentiable functions, but differentiable functions means that I can write df dx1. I can take the partial derivative of the function with respect to x1. I can take the partial derivative of the function with respect to x0, with respect to x2, and with respect to x3. I can take those partial derivatives, and symbolically, I'm going to write that as d1f, d0f. I don't know why I did 1 and 0 out of order, but d2f and d3f. This is simply symbolic notation that I'm going to use to represent these partial derivatives. It's commonly used in general relativity. It's commonly used in mathematics. Well, more in physics than it is in mathematics, actually, but it's very common notation. And if I want to speak of these in sort of an arbitrary way, I'll just write d mu f. And that always is intended to mean df with respect to x mu. So if mu is 1, then it represents d1f, or the derivative of x with respect to x1. And what's important to understand about this notation is that when we use this form of the notation, this actually contracts just like a space-time index would. So if you ever see d mu f times, say, a mu, you know, whoops, I got to get rid of that line, you know that you can Einstein sum on these two when it's in this form. So the fact that it's sort of an upper index in the denominator makes it a lower index out here, and as a lower index, it's consistent with the Einstein summation convention in that case. But that's not really what we're here to focus on. But that's the notation we're going to use for these little differential operators. The point is that the differential operator of 0, say d0 of f, if I add that to, say, d2 of f, that is the same as creating a new differential operator called d0 plus d2 and acting on f. And it is also true that if I take a constant and multiply out here by, say, a, and a constant out here by, say, b, those constants will live in here like that. And if I say a d0 of f plus a d2 of f, I can get a d0 plus d2 of f. And so d0, d2, we know acts on f in a straightforward and linear fashion, because that's what this rule really says. So I can create a new differential operator, and I can call it L. And L equals d0 plus d2. Or if I have those constants in there, it could be a d0 plus b d2. So these so differential operators are linear, right? They are linear. They can be added together. They can be multiplied by real numbers. And of course, they obey all of the rules of vector product spaces because there are opposites, right? L plus minus L equals 0. So any arbitrary linear operator can be written as a d0 plus b d1 plus c del 2 plus, I don't want to use d, I'm going to use e, all right? plus E del 3. That equals some linear operator, right, L. And the set of all possible linear operators is really the set of all objects of this structure. And if I add two linear operators together, I get another linear operator. And the rule to do that would be, say, A d0 plus B d1. If that's one linear operator, and I wanted to add to it E d0 plus F d1, I would simply get A plus E d0 plus B plus F d1. So these linear operators, this is, if I call that linear operator 1, and this linear operator 2, linear operator 3 is very, very well defined in a perfectly linear fashion. So, because of this, linear operators, the set of all linear operators that act on any function of 4 variables, right? Linear operators that's capable of acting on a function of 4 variables. That set, this set here, is a vector space. Right? It is a vector space. And right now, it's not an inner product space. It's just a straight-up vector space, right? And this is important to understand because this is a realization. It is a realization of a 4-dimensional vector space, a 4-dimensional real vector space. And it's a realization because these linear operators aren't just abstract symbols like these E's were. These E's define a vector space in mathematical principle, but these things here define an actual mathematical object that is a vector space. And it's a vector space of linear operators. And it's funny because the function itself is sort of irrelevant, right? Because I'm talking about taking linear operators and adding them together. I'm talking about taking linear operators and multiplying them by real numbers. I'm not actually using the linear operators to find anything out about the rate of change of a function. I'm not taking any derivatives. All I'm doing is creating operators, meaning this is a set of objects that you might consider tools that work on functions, right? These tools work on functions of space-time, of 4 variables, but I'm sort of interested in the behavior of the tools. And again, we're in this sort of circumstance where, just like maps, you have to start thinking of maps as their own little objects that can be added and subtracted and collected into toolboxes. This is the same way. This is like a bunch of tools that normally work on functions, but the tools themselves have their own properties and their own sets, collecting them together. And that set is a vector space. And the reason these tools are so important is that it's going to allow us to create a model of space-time that binds together everything we've learned, and we're going to discuss that briefly right now. All right, so we're not going to go very far into this model, but we are going to get started. And the way we're going to get started is now I'm going to talk, instead of about vector spaces straight up, we're going to talk about space-time. And we're going to use this sort of canonical picture of space-time, which I'm going to probably draw a lot of in the next bunch of lectures. And it's going to kind of look like this. These are coordinate lines. Every point in space-time is, we can give it a name like P, or Q, or R, or S. So every point could have its own name. That's one way of, and if we give an infinite number of names to all the points in space-time, that's a way of labeling everything in all of space-time. Of course, the way we name points in space-time is we actually give them coordinate values. And these lines here might be lines of, say, x1, the x1 coordinate. And these lines here might be lines of the x2 coordinate. And I'll only use 2 of them, but we also know that each of these points also has an x0 coordinate, sort of a time coordinate we'll call it eventually, and it has an x3 coordinate which we just don't even show. And this is just a quick way of me showing a bunch of points in space-time labeled by coordinates. But every point has a coordinate x0, x1, x2, and x3. And we call the coordinate of that point, I'm having trouble with this device today. Let me see if I can fix that. We call the coordinate x mu. Now when we do this, this is just a label of coordinates, and the reason that we put it in sort of the up position is not because this coordinate mu, that x is some member of a vector space, right? If it was, it would have a basis vector with it, right? This is just our way of labeling the coordinates, and eventually we'll get used to this fact. But x with the superscript there is not a member of a vector space. This is a way of writing down in shorthand for the fact that we're dealing with 4 different coordinates. And the idea is that we're going to substitute mu for 0, 1, 2, or 3 from time to time. So now we have coordinates in every point in space-time has a coordinate. And look, we don't need to think too much about, this isn't general relativity yet. Just think of a nice empty space, like maybe special relativity type of space-time where it's all flat, or it doesn't even have to be. The point is you have the real world is you have a manifold of points, a 4-dimensional manifold, and all the points are labeled in some coordinate system. And we're not going to get too specific yet about what the coordinate system is. Is it spherical polar? Is it oblate spheroidal? Is it Minkowski? Is it pseudo-Riemannian? All that stuff is beyond our ability to discuss right now. Right now, I just want you to see that we have coordinates all throughout space-time. But once we have coordinates all throughout space-time, once every point is labeled by a bunch of numbers, and these are numbers, and these are real numbers, by the way, we can immediately consider the idea of creating a function on space-time, right? We can take arbitrary functions of these coordinate values and produce real numbers. I could create a function that goes something like e to the x0 times sine x1 plus 3x2 quantity cubed divided by x3, and as long as I stay away from some dysfunctional values, I'll get real numbers out of this. I can create those functions at will, right? And I don't need to worry about specifying it. I can just assume that they're out there. I can even consider the set of all possible functions, right? I could say I want to consider the set of all possible real functions of 4 variables if I wanted to. But the point is that functions on the space-time will exist. So now, before we end this lecture, I want to say how we're going to now integrate what we've learned about vector spaces with this notion of space-time and its coordinate system. And the way we do this is, you saw me write these boxes down before, where I said, we're going to create a vector space, 4-dimensional, real, with a certain basis. And we did that, and we created this one vector space. Well, now, what we're going to do is we're going to forget this abstract notion of a basis vector, right? And we're going to replace that with the realization we just made, del mu. So the basis is going to be these differential operator symbols, del mu, which do in fact represent the rate of change, the partial rate of change with respect to these various coordinates, right? And this basis is formulates this basis here is now going to be the structure that builds our vector space. It's going to be the realization we use to actually talk about vector spaces. And then the most important part to understand is we're going to create one of these for every point in the space-time. Every single point is going to have its own vector space with its well-defined basis, and it's going to be 4-dimensional with a real number. So whenever I build this object, you have to realize that at every single place, I'm going to have erected a vector space at every single point. And there's a lot of points in between here, right? There's a point here, and a point here, and a point here, and a point here, and a point here. All these points. Every single one of them is going to have its own vector space attached to it. Every single one. And I'm going to spend a lot of time building each vector space because I have to I got to draw each point and I got to put a vector space there. There's not enough time in the world to do this, right? And I've decided that at each vector space, at each point, it's every vector in these spaces are bound to the spaces, right? These spaces have nothing to do with one another, nothing at all to do with one another, except for the fact that their naming of each space is established by the coordinate of the point it's located at. So if I'm going to talk about a vector space now, I say, I'm talking about a vector space V. That's not enough. I have to write down the point that that vector space is attached to. I have to kind of write V and then say x mu, or V z mu, or VQ, or VP. Right? I have to label each vector space with the point it's attached to. Otherwise, you don't know what I'm talking about. If I just say, oh, take the vector space V, well, look at them all. There's an infinite number of V, an uncountably infinite number of V in space-time. Every single point has its own vector space. And it's actually worse than that, because once you have a vector space, you have a dual space. And once you have a vector space and a dual space, you have an infinite variety of tensor product spaces, and all of those exist as well. Now, what I haven't done is I haven't said, oh, each of these are an inner product space. I haven't established a metric for each of these, but yeah, I have to think about that too, right? But what we've just done is we've taken our first step into understanding the architecture of general relativity. General relativity uses what I've just drawn here, all of this dizzying structure of an infinite number of vector spaces, one located at each point of space-time. That is the foundation that makes up the entire subject. Understanding how the inner products are going to work on all these vector spaces is actually the very kernel, the very core of understanding general relativity. And binding these vector spaces together in a logical whole, getting control over this, is really what the subject is all about. That's actually what the subject of differential geometry is all about. And it's probably what we're going to be talking about for the next several lectures. But this is what we have to start imagining. You have to know that when I write down a coordinate system like this, I'm immediately saying every point in space-time has a label. The label has got 4 coordinates to it. And every one of those points has its own vector space in it. Every one of those points has its own vector space, dual vector space, infinite number of tensor product spaces. And ultimately, yes, every point will have its own inner product. And the basis for all of those vector spaces is going to be these differential operators. These differential operators that would act on functions of the space-time. That's how we're going to describe a vector in the vector space. In other words, any vector in a vector space is going to be A mu del mu. Just like it used to be, A mu, E mu. We're just replacing the E mu with the del mu. And there's a good reason for that. We'll talk about that in our next lecture, about why we're choosing that particular realization. But we have to now use an actual realization of the concept of a vector space in order for all this to work. Okay, so that's how we get started. That is the architecture that we're going to now bind together. We're going to analyze, understand, and expand, right? Because, for example, I haven't told you about the basis vectors of the dual space. I haven't told you about the basis vectors of the tensor product spaces. Although you can, although it's not difficult. No single step in all of this is difficult, right? Getting to where we were, that this makes sense, we had to run through this whole notion of how vectors worked. We had to understand how to create a realization of an abstract vector product space. But once we understand that, understanding that every place in space-time has coordinates, that's not hard. Understanding that every point in space-time has its own architecture of vector product spaces, covector spaces, tensor product spaces, basis and inner products, that's actually a little bit weird, because that's pretty freaking, that's a lot of density. There's a lot of mathematical density. Every point, I mean, remember, points, there's an infinite number of points between any 2 points, right? I mean, it's not just an infinity of them. It's like an uncountable infinity of infinities. It's just a lot of vector spaces. But we will find a way to talk about them all at once. And the reason we can talk about them all at once is because we're going to introduce the concept of fields. And once we introduce that, we're going to understand that this infinity of spaces can all be kind of collected together, and that'll be the subject of our next lecture.